I'm Danielle. I'm looking at Morse theory. So similar to Tom, I'm not looking at a specific paper, but more just the theory. So what I'll be looking at is a lot more images and looking at different figures and seeing how they kind of morph from one to the other. So a lot of homotopy equivalent shapes and how they kind of convert. So we'll be looking at just kind of an introduction to what Morse theory is, a basic example of kind of what type of critical points we'll see, which is kind of the main theory behind Morse theory, is looking at these critical points, and a formal definition, followed by some interesting gluing of the shapes, how they kind of convert from one to the other with the homotopy equivalent shapes. So Morse theory involves analysis of the topology of a manifold by studying differentiable functions on the manifold. So a typical differentiable function on a manifold will reflect that topology directly. So the theory can be used to find CW structures and handle decompositions. So handle decompositions are kind of, as they said it, are to smooth manifolds as CW structures are to the topological structures that we looked at. So what we're going to do is I'm kind of going to go through what we're going to look at and then show the images after. So what we're looking at is if we assume a landscape M where we're going from a function f to r. So f sends each point to its elevation. So before I show the image, I'll kind of put an image in your mind. Think about just like a saddle, if you put like a saddle on a horse, or any sort of like mountainous landscape is what we're going to be kind of thinking of. The inverse of any point in R is a contour line. So the idea behind that is like a topographical map, which actually was the initial start of Morse theory, was actually by, I think it was Cayley and Maxwell, who looked at topographical maps. So they were the ones that kind of started this idea into topological spaces. So what we're going to be looking at is how the topology changes if the region is filled with water. So actually, if you think of a mountain and it's flooding, or a saddle and the area is flooding, as that water fills the area, how is the topology going to change? So when we see a change, it's going to change when it fills the basin. So think of it just as like a prairie almost with peaks on either side. As it fills that up, the topology will change. As it covers the saddle, or like a low mountain pass, and as it submerges peaks. So this was just a simple contour map to get you to think about the idea of the mountain pass and the inverse image that I was talking about. So this is a saddle. The main point of this is to kind of look at this saddle point, and what we'll get into next is the critical points, and the saddle, this point here is actually known as a saddle point, which is one of the critical points that we're talking about. And what we'll be looking at, which is why I liked these images, is if you look at the line that goes, we'll consider that kind of the y direction, positive and negative y-axis. That direction versus the x-axis direction is the most important part that we'll hit on, which is how Morse theory kind of develops. So those 3 points that I just mentioned correspond to the 3 critical points. The basins are also known as the minima of the graph. The saddle points are just saddle points. And the peak are maxima, as kind of you would expect. So we associate an index with each of these critical points. And so that's going to refer back to the x-axis, y-axis image I was talking about. So the index of a critical point B is the number of independent directions around B in which f decreases, respectively with the above list. So what that means is, with the saddle point, I'm not going to click back because it's like 100 clicks, but in the y-axis we looked at, where the graph decreased around the saddle point, that would be an index of 1, because in that one direction, it's decreasing. So it has to decrease both ways, so like say positively and negatively on the y-axis, it has to decrease for there to add 1 index to it. Versus the other side of the saddle point, it went up, so that doesn't apply. So each of these points, the minima have an index of 0, saddle points 1, as I just described, and the peaks have an index of 2. So the basic example we're going to look at, just to get a little bit more mathematical to it, we have the landscape M as we talked about, and the inverse map from -infinity to A, where A is the, I guess, the elevation that we're looking at. So we're going to look at it as the topology changes as A increases. So our example that we're looking at, which is kind of easy to see, is a torus kind of stood up. So what I'm going to refer to, and again, sorry, I won't click back because it'll take a little longer, but if you remember that this point is going to be considered as P, this elevation will be considered Q, R, and S. So those are going to be our 4 critical points. And as we'll consider again, that think of it as the, we're filling up the torus with water. So we'll fill it up slowly, and the topology will change as it's increasing. So as if A is less than P, then MA is the empty set. So that was that point right at the bottom. Obviously it doesn't increase or it increases around that point, but it's just flat, nothing's going on, so it's just an empty set. So when A is between 0 and Q, so Q is that first point at the bottom of the, say, the donut torus hole, that can be considered as a disk, right? So if you thought about just that image, as you're filling it up, it's just going to be equal to a disk. So it's not going to go past that bottom of the circle yet to make kind of 2 sides to it. It's just going to be filling up almost like a hole. So we'll say obviously that's homotopy equivalent to a point because as it shrinks down and as it's filling up, it goes from the size of a point up to a filled up hole. Then between Q and R, so that was between the bottom of the cutout circle of the torus to the next one, and not quite hitting that next point is considered a cylinder because as it fills up, you get the 2 sides of it, which means you could, if you thought about it, kind of flipping it over and straightening out, it would be equivalent to a cylinder. Or you could also say it's homotopy equivalent to a disk with a 1 cell attached. We will see an image of that next, and so that is the same as taking the bowl we had from between 0 and f of q, and taking that bowl and attaching just like a handle to it almost. So that's that kind of image. The next one is between R and S, so that's between the top of the circle to the top of the torus. So when that fills, we'll say that's a homotopy equivalent to either a torus with the disk removed, so the top part just kind of cut out, so it's filled up, doesn't quite hit the torus yet, or it's a cylinder with 1 cell attached. So this is the same as taking that cylinder we had, it's filled up to the sides, and just putting another handle on top of that part. And finally, it's just anything greater than S, it's just going to be the torus. Oh, I'm sorry. The rule we have here that we'll create and actually end up disproving it is that we're thinking right now, based on these answers, is that the topology will only change when A passes the height of a critical point. But we'll see, based on a counterexample, that's not quite true. So these are just the 2 images, so you can actually see what I was just explaining. This is actually the second thing I was talking about. So this is the cylinder with the 1 cell attached. So this is between the R and S heights, and this is between the P and Q heights. So, as I just said, the rule that we stated is actually false. So let us consider that our landscape is x cubed, where, as we know, 0 is a critical point for x cubed, but the topology class doesn't change when A passes 0. So the problem is that the second derivative is also 0 at 0. This means that this is a degenerate critical point. So as you can imagine the graph of x cubed, it decreases on one side of 0, but increases on the other. So that means that it's degenerate because even though half of it is what we're looking for, the other half obviously does not apply. So as I just said, it's unstable. You could think about it as if you kind of rotate the axis, rotate the figure, you could turn it into removing that degenerate critical point or turn it into 2. I'm not going to try to explain that in image, but you can try to picture it yourself and how that would work out. The other example I'll show next is a monkey saddle, which is kind of just a 3D figure version of the x cubed. This is just the monkey saddle. And again, if you were to look at it going up this way, it would look like that is going to be a non-degenerate critical point because it, decreases in this way, which is what we're looking for. But as it increases the other way, that's what makes it degenerate. So this is just the formal definition, which is just saying that from M to R in a differentiable manifold, the points where the differential that vanishes are called the critical points, and their images are called the critical values. So that's just going through the formal definition. And what we see, which is the most important, is that it's not degenerate if C is not equal to 0, and degenerate if C is equal to 0. And this is just saying that the index of a non-degenerate critical point B of F is the dimension of the largest subspace of the tangent space to M at B on which the Hessian is negative definite. And the Hessian, if you recall, is just a square matrix of the second partial derivative. So that's kind of the next important part that kind of comes from this. This is just kind of a fun example, which is the hot dog. So this, you can see, has 4 critical points as well. It has the one right here at the bottom, and that's, again, that has an index of 0 because it's the bottom of the image. It stays flat. It just increases around that point. Nothing else. The top here will have an index of 1 because you see it decreases in both negatively and positively y-axis. And then the other 2 at the top are going to be index of 2 because they decrease in both ways. Finally, I'll just touch on this. This is a fundamental theorem of Morse theory, which this is the kind of gluing I was talking about. It gets a little more technical in this definition, but the basic idea of what we're looking for is saying that, like the images we looked at before, if you take the disk and then attach a 1 cell to it, that's going to take it to a cylinder next. And as you add those kind of handles on, or add the dimensions as they go up, you can go from one homotopy equivalent shape to the next. Which, again, the example here is the torus. And so this just shows all of the images I was looking at before kind of put into one. So you start with the cylinder, the disk, as you start to fill up the bottom of it. And then as you reach the next section, you're going to add a handle, and that'll make it come to the next point, and then so on and so forth. It slowly morphs as you glue kind of one edge to the other. It becomes the torus in the end. And those are references.
Great. Thank you. Any questions? Questions? All right. So, quick question.
Mm-hmm.
So, when you said the rotating the x cubed,
Yes.
could you maybe sketch
Yeah, I can try
what would
to.
happen?
Okay.
I realize sketching is a little tricky, right?
Yeah, so if you went from
Would you mind using the markers? It shows up better on the video.
this screen work?
Yeah.
Okay, so this is the normal graph of x cubed. What we're trying to do is get it to that. This is obviously our critical point. This is considered that x equals 0. And this is the critical point, but it's degenerate currently. So what you would try to do is rotate it so that you get like this, right?
You're too far.
I'm too far?
Too far. 45 degrees to do it.
Right. Oh, yeah. So.
Sharp axis.
Because you want.
Yep. Good. There you go.
Yeah, okay, so if you now you're looking at this point here, yeah, it increases in both ways here. So right now, it's has an index of 0
Yep.
because it's the bottom of 2 increasing sides. Then if you were to take it and actually flip this over, or just rotate it 180 degrees, it would make it so that, like that, I believe, something like that. And this would be the critical point now, which has an index of 1 because it decreases in both ways, and it's a non-degenerate critical point because it goes down in both directions. And then you also see, which is what I was talking about, where you can turn it into 2 critical points. So now you see another one. It might be a little off because of the flipping, but this would have an index of 0 because it increases in both ways. So that's kind of the transition you can make.
Other questions? Great. Thank you.